Thank you, Matt. Actually, the last talk from the ByteDance colleague has stole a lot of ideas from my talk. Just kidding. So we do have a lot of overlap. So my topic is the real-world torch compile practice from our team. So let's begin. First, let's introduce a little bit of our team. We are the compiler and runtime team at Alibaba Cloud. Our team's mission is to optimize the core frameworks and the infrastructure that powers everything from our internal service to the ICE and fast products our external customers rely on. Essentially, our job is to make things run faster and more efficient on our cloud. And this fundamental drives the performance is precisely what leads us to explore and push the boundaries of torch compile. All right, so let's quick align on what torch compile is. As you know, the dream is simple. You take a standard PyTorch model, like the mine model here on the left, then apply torch compile on the model. Torch compile will compile it for you, generating an optimized model with the same output as the original one. It's not illustrated here, but backward can be also optimized as well. So what's the magic behind this? Basically, torch compile involves three components as the red part. It uses dynamo to capture graph, AOT autograde to handle backward passes, and inductor to generate optimized kernel from the captured graph. So the promise is fantastic. A guaranteed correct speed up from one line of code, all thanks to this sophisticated pipeline. But what happens when this clean ideal picture meets the messy reality of the production model and training frameworks? That's why our really work began. So when we move from the ideal picture to our production environments, our challenge boiled down to three main areas. First, we immediately ran into conflicts with essential optimizations that our team rely on. Torch compile doesn't exist in vacuum, and get it work with critical tools like Deep0 for distributed training or with gradient checkpointing for saving memories was a major initial hurdle. We call this the ecosystem tangle. Second, we focus on what we call the last mile to optimal kernels. This is also stable but important issue. Even when torch compile ran successfully and gave us a solid speed up on eager mode, which is already a win, we found that we still leaving performance on the table. This happens because small unrecognized patterns in the user code can prevent the compiler from creating the most efficient fusion. So the challenge wasn't about fixing something that was broken, but about closing the gap between a good speed up and an even better one on enabling these smarter kernel fusions. Finally, we had to manage the runtime overhead. The benefits of compilation are not free. We saw significant performance stale from recompiles when input shape changed, and a noticeable startup latency, which in some case made the compile model slower than eager mode. And now let's look at each of these more detailed, starting with the ecosystem conflicts. Our user employs a diverse range of technology stack for their training jobs. To make the ecosystem challenge we face on concrete, I'm going to focus on one representative and very common example, the use of Deep0 often, and if not always, paired with gradient checkpointing. Now, the initial problem looks like below. The code wasn't crashing, but it ran without errors, but we saw no speed up at all. The compiled model was just as slow as the eager one, which completely defaults the purpose of using torch compile in the first place. This was mysterious at first, so we had to dig into the logs of torch compile to diagnose the issue. And when we saw this, we found that the graph break caused deep speed operators, and there's more critical log indicate that gradient checkpointing is not supported by dynamo, as you can see on the screen. This means dynamo was consistently giving up on tracing checkpointed module and falling back to regular Python execution. So while the program ran, we weren't actually compiling the parts of the model that matters. The challenge wasn't fixing a crash, but re-architecting the integration so that the compiler could actually see the full graph and do its job. So our solution was a two-phase process focusing on just making it work and then making it fast. In phase one, we focused on fundamental compatibilities. We patched dynamo to correctly understand and handle torch checkpoint, and at the same time, we taught it to identify and skip some deep speed communication ops that were breaking the graph. To make this solution widely available, we submit to the DeepSpeed integration to Hugging Face transformer and accelerate libraries. So users can just use the torch.compile arguments to use DeepSpeed with torch.compile. So at this point, the module ran without compiling graph break or higher order ops a lot. That's a huge milestone. Phase 2 was all about performance. We found we could skip even more DeepSpeed ops than that were redundant in the compiler context. We also developed a heuristic to automatically identify the best units to compile, which allows torch.compile to create a large fused region within the graph. And finally, we updated the default 0 per fetch arguments, ensuring our data pipeline could skip up and efficiently overlap communication with the now much faster computation. By leveraging this target optimization on the top of fundamental fixes, we finally achieved a system that gave us the best of both worlds, the memory efficiency of training ecosystem and the speed of torch.compile. So let's talk about the last mile to optimal kernels. While torch.compile often generates good kernels, we found some common situation where it's leaving performance on the table. Today, I will walk through 2 case studies related to the scale.product attention, the SDPA function. The first case involves a custom version of attention that used an Alibaba bias with a default compiler didn't know how to optimize into the single kernel. The second case deals with a simple but common scenario where an empty attention marks was given and preventing the use of even faster hardware backend. So let's dive into the Alibaba case first to see how it's handled. As the diagram shows, the user's code calculates attention by adding a scaled Alibaba bias and a standard mask together before the softmax. This is a perfectly valid way to write an attention. However, torch.compile's pattern matcher is very specific. It does not yet have a rule to recognize this combined Alibaba plus mask structure as part of the fusible attention block. Because the pattern doesn't match, it gave up on high-level fusion and fall back to the default mask implementation, and torch.compile will compile each operation separately. Our insight was that from a logic perspective, the combined B multiple with Alibaba plus mask is just a single finite bias mask. We realized we could teach Dynamo to see it that way. So we implemented a custom pattern match path. This path identifies this exact struct in the graph and rewrites it to use the canonical memory efficient SDPA implementation, treating the entire Alibaba plus mask expression to a single valid attention mask. And this gives us a 30% speed up comparing with the default mask implementation and total 260% faster than the original eager mode execution. Our second last mile case study is different. It's not about recognizing a complex pattern, but about simplifying a simple one to unlock the absolutely better performance. We started from good place. So many of our model was already compiled and with the standard SDPA kernel, which is memory efficient. However, we knew that there's another level of speed up. The problem was the attention mask. The SDPA function is a dispatcher and its fastest backend flash attention has very strict requirements. One of these is that it cannot be used with arbitrary mask, even if the mask is full of zeros. Our key side was that many of the important use cases like inference on unpadded data, this mask is always 0 and therefore redundant. So we implemented targeted constant folding paths. This path run before the main compiler inspects the mask tensor, and if it can prove that the tensor only contains zeros, it rewrites the graph to replace the tensor input with a simple null value. So this simple change, swapping a tensor from zeros to null, it satisfies flash attention's prediction, allowing the SDPA dispatcher to select the fastest path. So this optimization gives us additional speed up and without changing the user's code. So finally, let's touch the challenge of runtime overheads. This is a very topic, but I want to share one concrete example of how we tackled unnecessary compilations. The root cause was very subtle. To ensure correctness, torch.compile create guards on the properties of your inputs. One of these properties is the memory alignment. In our use case with dynamic shapes, sometimes the input would be aligned to a multiple of 8, and sometimes it wouldn't. This constant change in the alignment property triggers the guards and force an expression recompile, even though the SDPA kernel itself could handle either case perfectly fine. Our solution was to make this alignment property consistent. We implement a change to the pad all inputs to a multiple of 8 before they are passed to the compiled function. Because these inputs that torch.compile now sees is always aligned, it has no reason to create a guard on the property anymore. We effectively eliminate the recompiles by removing the source of the variation. So this patch has reduced the recompiles from 7 to 3 in our benchmarks. And this is a great example to how to understand the compiler's internal guarding mechanisms. And this allows us to make small changes that lead to significant real-world performance improvement. There are also other fixes and overheads related to the overhead. That alignment fix was a great win, but it's really just a piece of the iceberg. So for my final contents, I want to briefly touch some of the open problems and the future directions that was, and to the PyTorch community, and maybe we can have some good idea about this. First, on the dynamic shapes, the obvious solution to recompile is to compile a single dynamic kernel. However, this introduces a difficult trade-off. A kernel compile for dynamic shapes is less specialized, which means the Triton compiler can't make as many assumptions as the resulting performance can be slower than the specialized kernel. So the open question is when is it best to accept a slower general kernel versus paying the cost to recompile to several faster specialized ones. We believe this future isn't simple. In the future, this is not a simple switch, but a smarter cost-based strategy. So the next is startup latency. The first call to compile is blocking. We are actively investigating the work in progress asynchronized compilation feature in the upstream PyTorch. The idea is to run the first few iterations in eager mode while the model compiles in the background, hiding the latency. We think this is amazing and has potential beyond just start. Perhaps for hot swapping new compiled functions in the background without even stalling the main process. Another subtle issue is wrapper overhead. When a kernel isn't significantly faster than eager, say only 10% speed up, the Python overhead of dynamo, inductor, and the Triton kernel launcher itself can be a bottleneck. We've seen cases when this overhead actually leads to a new slowdown. Future work here is about making the overhead as less as possible. And there's also some kernel caching mechanisms. The current on-disk or Redis-based cache is functional but naive. And I think this is a major opportunity exists to bring this level of intelligence to PyTorch caching system, potentially creating a shared cache that dynamically reduces compile times for common model and GPUs. Solving these challenges is key to making torch.compile truly seamless and zero cost for any workloads, and it's where a lot of our future exploration will be focused. So to bring everything together, what are the main contents of our work? First, torch.compile is absolutely a game changer for PyTorch performance, but as we see, it's not a silver bullet or magic black box that works perfectly in every production scenario. Our experience shows that unlocking its full potential requires a multi-layered approach. First, you need to work on the efficiency as a compiler. This means writing target passes to help it generate better kernels or use existing ones more effectively. Our work on pattern matching and some other passes are perfect examples for this. Second, you have to focus on frameworks integrations. Torch.compile doesn't exist in a vacuum, and making it compatible with entire training and inference ecosystems like we did with DeepSpeed is critical. And some of you may also have seen the discussion on some inference frameworks, and they are writing their own kernels rather than using torch compiles. And finally, you must tackle runtime optimization to reduce overheads. Our work on eliminating unnecessary compiles shows how cruel it is to manage this cost to ensure you are getting a true net performance win. By working on all of these layers, we were able to successfully harness the powerness of torch compile in our complex environment. So that's all. Thank you.